We now take a very special problem called free fall. Free fall is just a very special case of constant acceleration where the kinematic equations are true. The only thing in this is that instead of having to tell you that the acceleration is 5 meters per second squared, if a problem is free fall, you know immediately that the acceleration is 9.8 meters per second squared, pointing straight down toward the Earth. So this is the thing that they don't have to tell you and that you have to know. Otherwise, everything about solving free fall problems is just like solving problems with kinematic equations for uniform acceleration. Now, when is the problem really free fall? Well, it turns out in the Earth it's not, because there is air resistance. So there's some assumptions, and these assumptions can be approximately true depending on the shape of the object and how the object is dropped. First, the body must be near the planet Earth. And by near, I mean that you cannot see the curvature of the Earth. So if you're in a satellite or the space shuttle and you're up in outer space, then you're not in free fall, at least as we're using the term here. Your gravity pull is going to be different. But in everyday life, if you drop a ball off, for instance, the top of a building at Tarleton, or you happen to hit a baseball off the bat, that ball, as it's flying through, or even in a plane, the Earth basically looks pretty much flat. So if you can't see the curvature of the Earth, that is, you're close enough to the Earth there, then you can assume that this is the case. The other requirement is that you must neglect aerodynamics. So we're concerned everything falling like a rock. This does not include airplanes. Basically, what we're saying is we're not considering any pushes or pulls, what we'll call forces in Chapter 4, except gravity trying to attract you to the Earth. All right, so first assumption, near planet Earth. Second assumption, neglecting all aerodynamics. Okay? Now, free fall has been an important consideration for lots of things. For instance, Leonardo da Vinci was interested in it because he was interested in the idea of flight and how not to be in free fall. But he also made his living not as a painter, not as a sculptor. He made his living largely as a military engineer. And in the time of Italy when he lived, there were a lot of wars going on between the various city-states. And by understanding the nature of free fall, he could understand the flight of artillery, that is, cannonballs fired through the air. And this enabled his cannonballs to be more accurate. He also was concerned about how to pull cannons around. This leads to his laws of sliding friction. Now, this made him very valuable. It also meant that a lot of people would fight to capture such a military engineer to improve their military. And so Leonardo eventually had to flee to France. Now, Leonardo did not get the law of falling bodies correct, but he did get the first one. And it's based on a classical argument that God would use perfect numbers, that is, numbers that are not having rounding, they're not fractions. Now, you might say, well, isn't 1/3 a fraction? And the answer to that is yes, 1/3 of a meter is a fraction, but I could think of a smaller measuring system that was 1/3, in which case, in other words, I could multiply by some integer, say 3, and then this is no longer got a fraction. So if I use a small enough measuring, I can get rid of these. These things that do this, that you can take the ratio of two integers, are called rational numbers. That's because God is rational, the idea. Well, there are some numbers that don't fall in this, as you may know. Pi is one. The square root of 2 is another. In fact, when the square root of 2 came out of the Pythagorean triangle, it led to anarchy and war and social unrest. And people would, in fact, did kill a person who spread this type of information to others. Well, in Leonardo's version, he knew that a cannonball traveled further, that is, fell further, the longer it was in the air. So here's what he said. If you drop a ball initially at 0 seconds, it's traveled 0 distance, and the total distance is 0. In the next 1 second, it will fall a distance of 1 some unit. Whatever that unit is, we might call it the Leonardo. And that the total distance is now 1 Leonardo, an integer. In the next second, it'll fall further. What? How much further? He said, well, the next integer. So let's say it goes 2 Leonardos. Now the total is 1 plus 2 gives us 3 Leonardos. The next it would go 3, and this would lead to 6 Leonardos, 10 Leonardos, so forth. This was a pretty good thing, and it predicted cannonballs accurately as long as the cannonballs didn't have enough velocity and stay in the air too long. In other words, it's approximation of the more correct formula. So he was very useful, but as cannonballs got better, it was obvious that this was not right. Galileo Galilei comes along. Galileo is after Leonardo, and he knows of Leonardo's work. Galileo says, no, Leonardo, you're not quite right. God's got a sense of humor. God uses only the odd integers. Now, he did this through not just by dropping balls as people. He did this largely through water clocks and using inclined planes. And if you think about it, one of the great difficulties is how to measure time. These people do not have stopwatches and such. So he came up with the idea of a water clock, and he could weigh the water. And because you could weigh things very accurately, you needed to weigh grain, you needed to weigh gold. People knew how to weigh things. The weighing it enabled him to get an accurate measure of the amount of time, provided the water flowed out at a constant rate. So he built the water clock. In Galileo's thing, in the first second, it follows some distance. We'll call that 1 Galileo maybe. So that's 1 Galileo. In the next, it goes an odd. The odd integer is 3. So now the total is 1 plus 3 is 4. The next, it goes 5. 5 plus 4 leads to 9. 9 plus 7 leads to 16, and so forth. But if you look at that, this is 4 squared. This is 3 squared. This is 2 squared. This is 1 squared. And this is 0 squared. So the total distance traveled, the displacement, is related to the square of the time. Now, whether it's exactly equal to or not depends on the units you use. If you use the Galileos, I guess they are. If you use meters, then you might have to multiply by conversion from Galileos to meters. What physicists do when they say that, they say it's directly proportional to the square of the time, meaning that it's not equal because there may be a conversion factor here. If you want to make something equal, then you say delta x is equal. You have to put some conversion constant called a proportionality constant in there. So this says if you double the time, you'll get 4 times the displacement. If you triple the time, you'll get 9 times the displacement. But it doesn't say exactly what the displacement is until you replace this proportionality with an equal and a constant converting based on units. And this constant is different whether this units are going to be in centimeters or meters or inches, given the time is in seconds. Okay? So, this is what he found. The displacement is proportional to the square of the time. Now, let's go back and assume for a minute something Galileo couldn't do. Let's assume that the acceleration is constant. And if that's true, we know about the kinematic equations. And I remind you that we have x minus x naught would be delta x, and that would be the initial velocity in x times the time plus 1/2 the acceleration in x times time squared. But if you're dropping a ball, as we were in our initial studies here, then, and by the way, this is the positive x direction in our work here, then Vx naught would be the speed that it has, and it's dropped means it has no speed. So what we find is that delta x is equal to 1/2 times whatever the acceleration in x times time squared. At least that's what a constant acceleration problem would give us. But that's basically what we have with Galileo's law. We have some constant here, 1/2 the acceleration being a constant, times 1/2 would be equal to this proportionality constant here with a time squared. So by comparing the work of kinematics and Galileo, we see that the proportionality constant k is whatever the acceleration is due to gravity divided by 2. I remind you a couple of useful things in general about kinematic equations. If you're doing kinematics on a position time graph, in general, you have something like this, a parabola, and you can describe that by some t squared plus some b times t plus some c. That constant there is x naught, the initial position based on your coordinate system. This is whatever your initial velocity was, and this thing right here, that's 1/2 the acceleration. So in Logger Pro, if you take a set of data and it fits a parabola, this constant is 1/2 ax. This constant there is the initial velocity when time was 0, and this is the initial position based on your coordinate system. This is a universal truth for all kinematic equations. What we're saying now is, if we make positive be on the way down, and we start this from Vx equals 0, then this term will go away. This x naught we can make 0, or we can subtract it from that side. Then this thing here we would expect to be 1/2 of 9.8 meters per second squared, or in other words, if it's from free fall, you should get 4.9 meters per second squared for that constant of your fit. Will it? Probably not. There's going to be air resistance or something else. This is a model that approximates objects that don't have much air resistance. What have we found? We found that we know acceleration due to gravity for falling bodies from Galileo's work is constant. Galileo did even more. He went on and showed that all objects, regardless of their mass or how big they are, if they're falling bodies, will have the same acceleration. So this was different. People thought that heavier things might fall faster than light things. Again, if you watch the Mechanical Universe, they've talked about this idea that if you have a hammer and you had an anvil, if you think heavier objects fall faster to the earth because the earth pulls heavier on them, then this object would fall faster, this object would fall slower. But if we attach them to make a compound body, then if this object falls faster than that object, then this object would pull up and the total object would fall slower. However, based on the logic that heavier objects fall faster, the two of these together, if seen as a single object, is larger than the anvil, so they should fall faster. Thus, you get a contradiction in logic. The only way to get rid of that contradiction in logic is if they fall both the same way. Well, that's not a proof. This is part of this history of doing logic like God used the integers. But it turns out experimental work shows, in fact, it does. It was Galileo who pushed that experimentation, not just logic or statements about the nature of God, is what should determine whether or not an object has a particular law of physics. So, key point. Galileo's law of falling bodies. All falling bodies accelerate. I didn't say had velocity. I said have acceleration toward the center of Earth at 9.8 meters per second squared. This number, 9.8 meters per second squared, is given the symbol g. That's a positive. Whether the acceleration is plus or minus g depends on which way you rotate your axis. Whether it's x or y depends on how you label your axis. Read this law very carefully and do some serious thinking about it. In the next video, we'll come back and we'll talk about kinematics and solve problems.